Good morning, everyone. Hopefully that's not too loud. Sorry. Thanks for making the time to come along, or if you're watching this after the fact on Workplace, thank you for taking the time to have a look over it. It's sort of been on my to-do list for a while, this one, which is a bit of a talk about alarm management. And so I put together a slide deck and thought I might walk you guys through it, hopefully you find it interesting. A bit about why it's me up here. Apologies for the mugshot. But the point is that I've been an electrical engineer for 2 decades now, and I'm now a chartered professional engineer in ITEE and electrical. I am also a member of ISA, the National Society for Automation, and I've been actively involved in alarm management now for quite some time. The last 6 years of my career in operations, so it was 6 years about 2 weeks ago. And of that, the last 4 of those years were in alarm management. As a result, not surprisingly, one of my TA2 is against alarm management. So that's why it's me up here. So broadly speaking, I want to talk a little bit about human response versus automated responses, and hence why we have alarms. So why do we have alarms and why are they important? So when we start up and shut down a plant, we want to automate as much as we can, but sometimes it gets too complicated. And so ultimately, we need to have alarms and alert messages for operators to make decisions when they're starting up or when they're shutting down to handle those conditions. Also, when a plant is operating nice and smoothly, if something happens and there's a disturbance in the process, then obviously we need to alert the operators so they can do something about it, because not every outcome can be easily designed around. When we do our designs for our facilities, we try and automate the highest risk items. So the fastest response time items that we've got, we go through a HAZOP and LOPA process for looking for what is going to cause a major accident event, and we work backwards and say we need to definitely have a response in this period of time, a process safety time, they call it. And for that, we have a SIS control, a safety instrumented system. And these SIS controls have one job, that's turn off and isolate and make it safe. So the SIS is our kind of, in many respects, our first, our last line of defense, if you want to think about it front to back or back to front. I guess it's our last line of defense, depending on how you want to think about it. But it acts faster than any human can. Beyond that, we start looking at our process. So we see our temperatures skyrocketing or diving. Then we would say, well, we don't need to react quite so quickly. The process control and the DCS or the PLC, they can handle that. And so we would design the system to try and react to that. Failing that, we then have alarms that operators can respond to. So ultimately, it's layers of cost. Could you put absolutely everything in a safety controller? Probably. And I suspect it would cost so much money that you couldn't afford to actually finish building your plant. So everything's about balance and compromise. And the good thing about human operators is that humans are actually really adaptable. Surprisingly, scarily so. So operators can anticipate, they can learn, and they can head off problems long before they happen if they're given good information to work from. So that's a good thing. First thing with alarm delivery, assumptions. If an alarm happens and no one's in the room, did the alarm happen? So yeah, obviously that's a bit of a riff on the whole tree falls in the woods thing. And the fact is that if an alarm does go off and an operator doesn't see or hear it, then no, it didn't actually happen, because the operator doesn't have an opportunity to do anything about it. So it's important, an important critical assumption when we have an alarm, that we assume that an operator will see that or hear that and be given an opportunity to respond. So ultimately, it's expensive to coordinate and maintain the reaction time when you're actually out amongst the plant. So if you get a radio paging and you're on the far end of the plant, you have to go all the way up to the control room to do something about it, or even find out what the alarm was, because the radio page is generic. Well, the problem with that is that takes time. You don't know how long that's going to take. So you haven't got a guaranteed response time to that alarm. And hence, a lot of people look at what we do here as the way of the future, because you have eyeballs on it all the time. And that allows us to support a less than 3 minutes response time for our highest priority alarms. And that's really important because if something goes wrong and an operator gets and nips it in the bud early, then we can prevent our loss of production, and we can reduce our risk of having a safety or environmental consequence. And when we do our reviews in our workshops for alarms, we assume that that is the case. So I just said how wonderful operators are, and they are, but they are also human, and that means they get tired, they have bad days, and like all humans, they forget with time because you're too busy thinking about what's the next thing happening. Maybe you've got a new baby on the way, think about that. I mean, the thing is that we have to refresh our training regularly, and training therefore is a critical component of what operators have to do every year, sometimes more regularly depending upon the risk. And we have a trainer specifically for that, and we have a training simulator that we also use for that function. However, and this is the big however, is what if there's too many alarms shown at once? So many that you can't react. And I was thinking about, on the drive in this morning, I was thinking about, what's something that everybody pretty much in this day and age has to deal with a smartphone. Most people have got a smartphone. I'm very surprised if anyone in the audience or watching has a dumb phone. And I don't mean the phone itself is dumb, but you know, it doesn't get 100 messages a second from, I don't know, Facebook, Instagram, Twitter, Snapchat. Insert the name of an annoying app here. So in essence, everyone's had a little bit of a taste of, I think it's reasonable to suggest that everyone's had a bit of a taste of what it could be like by getting dozens of messages interrupting you in the middle of meetings, trying to have a meaningful conversation with somebody, and that's a problem. The difference is when we're operating a plant, the consequences are a lot worse if you miss that message, potentially. So, 3 Mile Island, is everybody familiar or have heard of 3 Mile Island? So 3 Mile Island, just for the catch-up for those that aren't aware, is a nuclear reactor, fission reactor, and it is, oddly enough, on 3 Mile Island, and in America. In 1979, it suffered a partial meltdown. And one of the reasons that it did was because there were so many alarms coming through, and this is the days before alarm printers. They had this modern control system. It actually had a DCS, and it had an annunciator panel, but it also had an alarm printer, dot matrix printer. This is going off, printing off every alarm as it happened. It couldn't print the alarms fast enough, and there wasn't enough space on the wall in the annunciator panel to have all of those alarm messages up. And so it took over an hour for them to actually get the current message that they needed to get, by which time it was already, well, practically too late at that point. And yes, there was a partial meltdown. So yes, permanent damage to that core. Could have been a lot worse. In any case, there was a study done following that, well, there were a lot of studies done. The US Atomic Energy Agency did a study, specifically a guy called the J.C. Williams in '86 found that there was an 11 times increase in error rates when operators were put under duress. And so ultimately, those error rate probabilities were validated by a standard that one of the ones that we follow. It's sometimes pronounced EMUA. I don't like calling it like that. It's EMUA. EMUA sounds too much like manure, which it isn't. It's awesome, but never mind that. EMUA 191. So they validated those error probabilities and how much a human being could process in terms of alarm information and actually have meaningful responses to. So that was released in 1999, which actually, so that's over 20 years ago now. And Milford Haven is an interesting case. So Milford Haven was an incident that happened in the UK, the Pembroke refinery. And what happened is that there was an electrical storm in the morning and caused tripping all throughout the plant. There were so many alarms going off that when there actually was a trip of the process, the operators were trying to get back online, they couldn't see, well, essentially the wood for the trees. There were just too many alarms on the screens. In fact, they had 2,040 configured alarms. The interesting point, though, is not so much the number, it's the fact that 87% of them had been ranked as high or very high priority, meaning that they were both visual and audible alerts. So operators basically had no idea, just information overload. And that led to an explosion. People were injured. Nobody died, fortunately. So ISA, I mentioned them before, the International Society for Automation. They took that EMUA 191 and refined it quite a bit and released their own version, ISA 18.2. And broadly speaking, that is the most globally recognised alarm management standard. And that's the one that we predominantly follow. So a decision was made for someone, ended up being me, to rewrite the alarm philosophy and to have more detail and essentially try and address our alarm problem. So in 2016, we rewrote that and we heavily follow the metrics in ISO 18.2 with a sprinkling of EMEI 191, particularly for standing alarm contributions. Oh, one other thing. The guidelines specify or suggest, EMUA suggests that 5% of your alarms, 5% should be high or very high, not 87% as per Milford Haven. Longford. Most people in process engineering or in oil and gas in Australia have heard of as Longford. So that happened also in the 90s, and alarms were also a contributing factor to that one. So for each of these, 3 Mile Island, no fatalities, as I said. Alarm print rate was 14 alarms per minute, which wasn't fast enough. Milford Haven, 26 were injured, no fatalities. And that was mostly by luck. I forgot to mention that incident happened on Sunday morning. That's the only reason there weren't any incident, any injury, any significant, any deaths, because there were simply not enough people. It was Sunday. And so far as SO goes, there were 2 fatalities and 8 were seriously injured. So the operators at Longford were subjected to 8,500 alarms per day on their panel. And if you study this stuff, you start to see a trend, somewhat of a disturbing trend, and that is that in the 70s to 80s to 90s and more recently, the more and more we automate, the more and more people add alarms, because I think that's going to be a great idea. Let's just add some more alarms, right? So each of these alarm counts for each of these plants is increasing with every incident because they're moving closer to us in time. So in the mid-90s, 8,500, and then of course, Pembroke before that was 2,000, and then at 3 Mile Island, it was less. So the point is that we keep adding more alarms as we develop and add more technology to our plants, and that's not always a good thing. So we did a lot of thinking about the most appropriate alarm metrics for us to choose, because there are actually dozens and dozens of alarm metrics, everything from alarm count per day, but in terms of operator response, it's generally accepted that alarm rate is one of the biggest problems, because that's the rate new alarms come in versus how much they're cleared. So that alarm rate per 10-minute period, and that 10-minute period is the reasonable amount of time we expect an operator to be able to respond or react to an alarm or an abnormal condition. So sometimes you'll see that expressed as alarm rate per hour. We consider 10 minutes because 10 minutes is that reasonable expectation for operator to respond. Because you might think, I've got 6 alarms per hour, which is the same as 1 alarm per 10 minutes. That's not true, because you could have 6 alarms in one 10-minute period and have no alarms for 50 minutes and still think you're compliant when you're not. Standing alarms is any alarm that's been standing there, not literally, clearly, has been on the screen for more than 24 hours. Sometimes referred to in ISA as a stale alarm. So different terminology, essentially the same thing. And they're bad because they clutter the screen up and make it harder to find what you're looking for. Percentage of time in alarm flood. Process engineers love this one. Not entirely sure why, but they do. An alarm flood means that you have had more than 10 alarms come in on a panel in a 10-minute period, and then in the next 10-minute period, it drops below 5 again. So it latches in at 10 and latches out at 5. So alarm floods are simply trying to measure how often I'm in a scenario where an operator has to deal with too many alarms at once. Okay, so there are plenty of other metrics, but there's none actually formally accepted or in use at this time. Some people have their own pet ones, but those are the ones that we use formally. All right, so a little bit about standing alarms. I hadn't already said 24 hours or greater, and essentially that creates visual clutter on the screen, which is a problem. And essentially, tracing those alarm histories on the current alarm screen becomes difficult if we have a high standing alarm count. And differentiating between long-standing alarms and currently received alarms can be difficult once you've acknowledged them. You have to actually dig in and figure out what time it came in, which can be difficult when you've got multiple pages of alarms, if there's a lot happening. So what does good look like? According to the standards, the best practice guideline is 10 standing alarms per panel. The goal is, for us, we've said, can we at least try and get to 20? If you actually pull the thread on the absolute maximum that they recommend, which is 30, that was set in EMUA 191. Thinking was that the screens at the time were not, these days we've got 24-inch screens. Some people have 55-inch 4K massive TV screens, but the point is that at the time, that was not standard. These were 17-inch, 19-inch displays. They couldn't fit more than 30 alarms on a screen. So the original thinking was, one screen full is enough, and you will shelve about 20 of those to get them off of your screen, and hence why they set a target of 10. So ideally there'd be 0, but realistically that's difficult to achieve. So how can we improve that? We can improve that when we get to a certain level by improving how much we shelve our alarms. So operators can improve to some extent their fate. Mind you, ask an operator to shelve 20 alarms, they'll probably do it. Ask an operator to shelve 600 alarms, and they'll probably smile, and I wouldn't blame them if they didn't. So that's one way we can actually reduce the number though, and that's valid. With correct authorization, we can alarm off. So let's say you've got a pressure transmitter out in the field, and it's dodgy for some reason. You can actually alarm off that particular instrument, and that will turn off and disable all of the alarms that come from it. Now, if you follow the correct approval process, typically we've been using auras for that purpose, and we flag it for maintenance. We know it's going to happen in 3 months' time, got to order a new pressure transmitter. That's okay. Or if it's worse than that, pick it up at the next TAR. And I'm assuming we can safely run the plant, of course, because that's what the aura's for. Is it okay to disable the alarms for this? And if it is, yes, do so. And then you'll wipe out a whole bunch of those alarms related to that instrument. And that's perfectly valid. And we do that regularly. Obviously, prompt repair of damaged or faulty field equipment. There's a perception that, we'll just get that in the next 28-day cycle. Like we've got other priorities and other issues. And I feel like sometimes there's a disconnect between the impact of that and the impact on our alarm contributions. So if you've got a faulty instrument in the field and you're an I&E tech, you might have a look at all of your stuff you've got to do today, and you say, well, that can wait. The I&E technician is not directly impacted by this, but remote operations or even local operations are by the excessive alarm contribution. So if there's a work order raised and you've alarmed off that device, then that's totally fine, leave it. Wait till the parts come in or you get spare time, that's okay. You've done the risk assessment, it's safe to do that. That's just some of the things. It's not an exhaustive list, but just some suggestions about how different parts of the organisation can help. Okay, my favourite one, average alarm rate per 10 minutes. So again, this has got to do with, as I said before, the analogy of 6 alarms in an hour is not the same as 1 per 10 minutes. So essentially, responding to high priority alarms in the required response time, this is essentially the distraction. So if you get a whole bunch of priority 3 alarms that come in very quickly and you get a priority 1 alarm, then you have to drop everything and deal with the priority 1 alarm. If you then have a bunch of priority 1 alarms that all come in a short period of time, do you have enough time to respond to each of them before your 3-minute response time is up? So this is why the alarm rate is a problem. And what drives that up is interesting, actually. We'll get to that in a second. But the current target for what best looks like is less than 1 per 10 minutes. We set our target at less than 2 because at this point in time where we're at today, that's achievable, I think. Best practice of 1, it's going to take a bit more. So how we can improve on those is root cause analysis of what's actually causing that alarm to go off. You'll often find that there's an incident that like one instrument will have a failure, it has a knock-on effect, and you'll get 4 or 5 other so-called consequential alarms. So what you can do is you can actually intelligently mute that and go back to the first alarm and say, this is one the operator needs to know. Show them that, and then mute the others. And when I say mute, you could just demote them so that they're logged as, yes, these events occurred, but they're not displayed to the operator. Because that's just cluttering their display. An operator needs to know what set off the chain of events. and they can look at the context in history as they're fault finding it. But showing that all on the alarm screen all at once causes an alarm flood, causes a high alarm rate, and that's not what we want. So you can also do things like tweaking the on and off delays. So in other words, when an alarm condition comes on, we wait 10 seconds just to ensure that it's not a communications issue or random glitch or whatever it could be, some noise. Some instruments are noisier than others. And you can, or you have like rippling of water level inside a tank. All of these things, I say water, I mean liquid. The point is that all of these things on delay would stop them from becoming a nuisance alarm. Off delay, same kind of thing. Hysteresis is dead bands. So in other words, the alarm latches in at a certain level and then it stays latched in until it drops below another level. And that stops that alarm from chattering as it goes up and down, above and below the set point. These are all things that we can do. Again, we circle back to prompt repair. So if you've got a dodgy instrument that's creating noise and it happens to be creating a whole bunch of alarms, prompt repair of that instrument, obviously that will also drop the alarm rate. And when we do new equipment designs, we actually workshop them properly and determine what their alarm priorities really should be. So one of the things that we'll talk about a little bit more towards the end is alarm workshops, why we hold them and how we do them. Percentage of time in alarm flood. So again, 10 alarms associated in a 10-minute period, latches that in, and then down to less than 5 in a 10-minute period on the same panel, latches that out. So again, similar to the one above, it prevents operators from actually acting on the correct alarm. Again, that target is 1%, less than 1%. That's considered best practice, and where our target is 2%. Much the same kind of things that we can do. Root cause analysis, prompt repair of equipment, and of course when we do our designs, we workshop them properly. So we did them manually in spreadsheets, and you can imagine just how well that went. So we started doing, in about the middle of 2016, started doing weekly reporting on our alarm rates. And in 2017, we started doing some initial deployments from our operator response workshops. Because in 2016, after the alarm technical spec was released to Rev 0, we did a whole bunch of alarm workshops on every single alarm configured. Took about 7 months, maybe 8, depending on when you count start and finish. But yeah, a lot of time, a lot of effort. So we started deploying some of that, and that included the reassessment of why is this an alarm? A whole bunch of alarms we demoted, they're just events. If I've got door of cabinet opened, that is not something an operator needs to be necessarily told. So that sort of thing got pushed down to an event. Anyhow, so alarm rates dropped, which was good. In 2017, following on from that body of work, some people may recall the Don't Be Alarmed project. Catchy title, not mine. Point is that that project focused on alarm rates, alarm flood, and made big strides in those dimensions. Following the reorg, there was a bit of a panel rearrangement, as in like the operator panels were rearranged, water treatment went out to site, and our model of how we actually, what was on what panel was tweaked slightly to adjust following the asset-led model restructure. And at that point, assets took over most of the responsibility. The Don't Be Alarmed project ended, and assets took over the driving down of alarms. One of the points that I think is really important to understand is that anybody who's involved with any of the plants that we operate, whether that's an I&E, whether that's you're an electrical engineer, process engineer, rotating, anyone who's responsible for any equipment or the design of that equipment or the maintenance of that equipment, where there is a flow-on alarm that's presented to an operator, you can contribute positively to helping us with this problem. Some more than others, clearly, but I think it's important to appreciate that everyone can actually help with this. So what we're trying to do is, assets are in the process of fine-tuning, and they continue to fine-tune the alarm on and off delays and hysteresis. We're adding more of this functionality to our wellheads and our kiosks. There's projects currently underway for that, and that will give us more levers for us to reduce the noise and make it easier for operators, and also to improve our compliance. So the OT team are monitoring backhauls, they test redundancy to ensure we have high availability of all of our connections between our sites. And we're also maintaining and integrating these alarm tools into our SCADA systems. There's currently a project underway to take the data from the master alarm database and pull it into an operator will be able to select the alarm and have all of the cause, consequence, and action information displayed in the same screen. So that hopefully will be delivered in the next 2 to 3 months. That'll be a huge win. Save them having to go and look it up in a separate tool that's currently only available on VLAN. Big time saver, especially for priority 1 alarms. We've only got 3 minutes. Operators, as we continue to drive improvements with, we'll be utilising shelving more regularly. And hopefully then we can collectively get the scores trending in a better direction. So for us, it comes down to the operator response workshop as a process and essentially understanding why we have to have it. So it comes down to this. If an operator can't do anything about it, why are you showing them? Every alarm that comes in should have something that an operator can do. And sometimes that thing is just pick up the phone and tell someone in the field, I have a problem, because they are not able to do a manual isolation. If that's the case, then fine. But the majority of stuff that we have designed and built functions remotely. It's intended to be. So therefore, for the most of our kit, if the operator can't do anything, then it should not be down as a visible alarm on the current alarm screen. So the operator response workshop attempts to quantify based on the plant, can a lack of response to this alarm lead to a train trip, an environmental loss of containment, safety repercussions. And from that, it then says, well, how long can you wait before you absolutely must act? And using those 2 variables, we figure out a priority 1, 2, or 3. So we've done that for every single alarm, pretty much. So when we do operator response workshops, the key thing is to have the right people in the room. Make sure that you've got someone that actually knows what causes the alarm, someone actually who does know what the consequences are. We made sure it was crystal clear in the alarm technical spec since then that is mandatory. If we don't believe that's been satisfied, we will reject the results. We won't allow the MOC to proceed. We asked for an automation systems representative. As an automation engineer, we tend to be the glue that sort of like takes the instrument alarm and passes it on through to the operator through the HMI. So we need to be in the room. We also ask for an operations representative, that is to say someone who is either an operator or representing the operators, so they know what an operator can and can't actually respond to. So that's critical as well. So if you have the right people in the room, it goes quite quickly, actually. If you have the wrong people in the room, you've got to open up a dozen. And when I say technical experts too, don't be afraid to pull vendors in, right? If you've bought an Emerson UPS and you're trying to plumb that thing into the system, like get someone from Emerson in. You want the right people in the room, otherwise you're wasting your time. I don't think I'll talk too much to this slide, but it'll be there for your perusal later. It's just essentially a basic workflow on the right. The full-size uncropped version is available, obviously. And we also try to classify our alarms to improve searching. So one of the things we did is we classified each alarm as being, let's say it's relating to rotating, let's say it's a comms alarm specifically, then you can actually do searches right now for those flags where they've been set and get a complete list of all of the rotating alarms, for example, on any one facility or all facilities. So we try to improve that as well during the review. So there's a wealth of information available on alarm management. This is not a new thing. And I was at a conference recently, and the overwhelming sentiment from several of the speakers is that alarm management is a solved problem. And I think that when they said that it was a solved problem, what they mean is how we improve is understood, all the standards are correct, all the targets are correct and make sense, we understand the problem. But that doesn't mean that we necessarily are where we need to be. So we do need to keep working on it, and we do need to keep our eye on the ball. Otherwise, it will get away from us. So the alarm technical spec is in open text, just like everything else. 100326767. It's scary that I know the CDN number, but that's what you get when you work on a document for 4 years. You can get in touch with me if you like, and of course, automation team. Most of the assets have been neck deep in alarms for quite some time, and they can all point you in the right direction if you need any help or if you have any questions. Awesome. Well then, with that, thank you very much for coming along. Thank you very much for your attention. And as I said, if you have any questions, please come and see me or anyone. And to see how you can help. We appreciate any help we can get. Thank you.